matrices in encryption and making messages secure. Philip? Thank you. If I have your attention this way, okay, you can come back to doing your quiz later. Yeah. So, if we take a message and I've said this is a secret message here, and put it into a cipher where each letter is represented by the number where it is in the alphabet. So T is 20, H is 8, I is 9, S is 19, and I've even left in spaces there for the spaces between words with zeros. So we get, this is a secret message, is 20, 8, 19, 9, 19, 0, 9, 19, 0, 1, 0, 19, etc. That isn't very secure. Anybody picking this up as a cipher would quickly spot that the zeros represent the spaces between words, and in an extended piece of text they know that the letter E is going to be the most common, so the number that comes up most frequently is the E. We can make it more secure by using a matrix. We chop the message up into a series of numbers, arrange them in a matrix, and then multiply them by another matrix. And this is a matrix, it's a random matrix that I got from using rand between, and just got some random numbers together to do the multiplication. And what happens then is that these matrices become a series of different numbers. You can see here, you can't see very well, but in proper matrix multiplication style, we've multiplied that number by that number, that number by that number, and that number by that number to get a result. And so on for each cell in the matrix. Okay? That number by that number, that number by that number, that number by that number. Okay? So then we can string the message back together and send that as our encoded, our ciphered, encrypted message. Okay, so T was 20, it's now 104. What's interesting, S, that is 19 there, is 93 in our encrypted format. The letter S now is 61. In the is here it's 72. Here it's 119, and there it's 100. So every instance of S is actually represented by a different number. When I first did this, I got the maths. Oh, good. So the S here in secret is 72, and the R there, also in secret, is also 72. So anybody trying to say, well, 72 is an S, is going to get it wrong. The whole thing has been mashed up so that it can't easily be understood. So, how do we get back from this sequence to the sequence that we're going to be able to recognize? And for that, you need the inverse of the matrix. The good news for you is that you only need to work out the inverse for a 2 by 2 matrix. We give you the formula of how to do the inverse of a 2 by 2 matrix. But this is a 3 by 3 matrix.
Is that 4 by 4?
There's 126 by 126. When you come to computers, they don't have the same restrictions. They can have whatever dimensions you like. So a 256 by 256 matrix would not be a problem. It would be a huge problem for you trying to calculate the inverse of it, but the computer can sort it out. Yeah. Yeah.
Does the computer have an automated way of calculating the inverse?
Does it have an automated way of...
Like, would you have to go through it, or would the computer know how to...
Well, you can program a computer, you can give the computer the instructions, the algorithm to do it.
Okay.
At some point, somebody has said, this is how to calculate the inverse. And so, if you go and look, you will find programs that will calculate the inverse of a matrix for you. But somebody has written out the algorithms for it. So, what we're doing, what this section does, is calculate the Gaussian elimination method, the inverse of the matrix by Gaussian elimination. And what you do is start with your original matrix and your identity matrix.
Can you turn off some of the lights?
Yeah. Now the identity matrix is, well, it always has the ones running down the middle of the diagonal and zeros in every other cell. Yeah? If you're going to use it in trigonometry, you will end up with the origin, with your identity matrix. And the Gaussian elimination method is to turn this matrix into the identity matrix by doing row operations. So you can switch the rows around, and you can add or subtract the rows, and you can multiply a row by a number or divide it by a number. Those are row operations. And the aim is to get to the identity matrix. So the first thing I've done in this one is to subtract the bottom row from the top row. So in this cell here, we're taking 4 from 3 to get -1, and here we're taking 3 from 1 to get -2, and 1 from 1 to get 0. Yeah? And we do exactly the same thing in the identity matrix. We take nothing from 1, nothing from nothing, and 1 from 0 to get -1. In this matrix here, I've taken the bottom row away from the middle row. So 4 from 1 is -3, 3 from 3 is 0, and 1 from 4 is 3. I've done exactly the same thing there. Now, a large part of this is actually guesswork. Here I've taken 2 times the top row away from the bottom row. So 4 minus 2 is 2, and in this one 3 minus 2 times minus 2 is minus 1, and 1 minus twice 0 is still 1. And every time I perform a function on this side, I do the same thing on that side. There is a large amount of guesswork in this. I possibly haven't found the most efficient way of getting to the end. But at this point here, I decided to switch those 2 rows around. So the minus 303 goes on the top, and the 1 minus 20 goes in the middle. And then I divided this row by minus 3. So minus 3 divided by minus 3 becomes 1. I've got 0 in there, and 3 divided by minus 3 becomes minus 1. And I feel I'm making progress at this stage because I'm getting zeros appearing in my matrix. I then divided, where did I divide? This one here, this row here, I have taken away, that's it, taken away minus 2.5 times the middle row from the bottom row. So 0 minus 2.5 gives minus 2.5 gives me 2.5. The minus 5 there, take away 2.5 times minus 2, or minus 2.5 times minus 2, makes 0 and 1. So, how many operations did I do? I did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 steps, 11 operations. I ended up with a matrix that is the identity matrix. And that's what comes of starting with a random matrix instead of one that would fall out a lot more quickly. And this is the effect of doing all those calculations on the identity matrix. So, if we then put those values in there, if this is really the inverse of that, when we multiply this matrix by that matrix, we should come back to that one. Yeah, we should come back to our original code. So, in this cell here, we've said 104 times 0.4286 whatever, 71 times minus 0.7143, whatever, and 61 times 0.4286, etc. And the result is 20. It's the number that we had originally. And in each cell, we've got the same values that we started out with. Yeah? So, this means that if you're sending a secure message, an encrypted message, you use this matrix to encrypt it, send your decryption matrix to the person who's going to receive it. In fact, you can send the original matrix and tell them to work out the inverse at the destination. And then send the message separately. They can sort out how to decrypt it. Yeah, Billy.
So how come the identity matrix works like that then?
How come this process works? Right, so you're starting here and making this become that. Yeah? And you're doing everything that you do to this, you're doing it to that.
Right.
Yeah? So if I had a sheet of paper and tore it in two, then I have folded it in half. It would be half as wide. So this becomes half as wide.
Right.
Yeah, you're doing the same thing.
So it's like reverse engineering.
Yeah.
So why did they choose the? Could it be any matrix? Could the identity matrix be any matrix?
No, the identity matrix is always ones down the diagonal and zeros in every other cell. That is what. If somebody says this is the identity matrix, it's got it's got ones in the diagonal and zeros in every other place.
Okay.
Yeah. It's a lot more important in trigonometry for manipulating images, Euclidean geometry. Yeah. So there we have another use of matrices in computing for encryption, decryption, etc. You have the matrix can encrypt your message. Working out the inverse of the matrix will allow you to decrypt the message. Yeah?
How do you find the identity matrix?
The identity matrix is always ones down the diagonal and zeros in every other cell.
Okay.
There is. If you took a matrix like, give me a random number.
7.
7,
5.
5,
5.
5,
3.
3. Okay. So if we multiply this identity matrix by this matrix, yeah, it becomes that times that plus that times that plus that times that. next row down and the next row down. So multiplying this matrix by the identity matrix gives you the same matrix, gives you an identical matrix. Does that work for two columns? Another random number, Hamza? 6. Philip?
3.
3 and 79.851. Okay. So we F4 that F4 that Okay, so whatever values you have in your matrix, if you multiply it by the identity matrix, the result is going to be the identity. You're not going to change the values that turn up in your at the end of your multiplication sum. Yeah. So that's what the identity matrix does. Any more questions?